Hello, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. For tonight, we're going to take a look at some applications of integrals using TI technology. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to introduce our two panelists tonight, Pat Flynn and Tom Dick. Pat has been teaching mathematics for 23 years. He's currently teaching AP Calculus BC at Olathe East High School in Olathe, Kansas. Pat is a 2013 Presidential Award winner for excellence in mathematics and science teaching, and he has served on the TI-Nspire authoring teams and was also a writer for the We All Use Math Every Day program in conjunction with the television show Numbers. Pat has presented at many international, national, and regional conferences in the areas of technology, calculus, and geometry. Pat, thanks so much for being with us.
Thanks, Michael. I'm real excited to be here.
And Tom is a senior mathematics advisor for Texas Instruments and is also professor and former chair of the mathematics department of Oregon State University. He has served on the editorial panels for the Journal of Research in Mathematics Education and the Mathematics Teacher Educator. He remains active in the College Board's Advanced Placement Calculus program and has previously served as chair of the AP Calculus Test Development Committee. Tom, thanks so much for being with us.
It's great to be here. Looking forward to the webinar tonight.
We're expecting a large crowd, so your audio is muted. Feel free to send questions to Pat or Tom throughout the webinar using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the certificate of attendance at the conclusion of the webinar. Once that recording is available, we suggest that that's how you follow along. That way you can go at your own pace so you're not trying to maybe do two things at once tonight. So just sit back and relax and enjoy. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the WebEx menu and choose Audio Broadcast. At this point, Pat is going to discuss our agenda.
Thanks, Michael. The first thing we're going to talk about is accumulation functions. We will be visualizing accumulation using a question from the 2008 exam. And then we will also evaluate integrals using TI technology using the 2016 practice exam that just came out this past year, number 77. We'll also look at a rate in, rate out problem from a past year's free response question and using TI technology with that. We'll also be looking at slope fields and producing slope fields using the TI technologies, the TI-84 and the TI-Nspire. And then we'll also explore a BC topic of Euler's method. Afterwards, we'll have some online resources, and there will be a webinar giveaway, Michael.
Thanks so much, Pat. And Tom is going to discuss our expected outcomes.
Thanks, Michael. So our expected outcomes are we're hoping you see a good illustration of how you can use technology like the TI-84 and TI-Nspire as an aid to understanding accumulation and accumulation functions, illustrating that use and investigating a rate in, rate out problem from AP exam. And particularly powerful use of technology is in generating slope fields. It's just kind of revolutionized ways people can visualize solutions of differential equations. And all along the way, you know, we'll be touching base with what students are expected to do when they're assessed on these topics on the AP exam.
Thanks so much, Tom. Pat, it's all yours.
Fantastic. Well, let's go ahead and take a look at our first screen, this one. Michael, are you able to see this okay?
Not just yet, Pat. You're going to have to go to that very top of the menu and share your desktop with us.
That's right. I'm so sorry.
No problem.
Okay. There we go. Okay. So the very first question I want to take a look at is from the 2016 VC exam. And it deals with finding, you're giving f prime of x, and you're told what f of 2 is, and you need to decide what f of 5 is. Well, when students see this, they should try to recognize that we've got an equation on the left-hand side here, and if we happen to take the integral of both sides, that the integral will result in the following equation here. And that's pretty nice, because we have what f of 2 is, and all we have to do is predict what f of 5 is. So we're going to rewrite this as a fundamental theorem of calculus question. We're going to put limits on our integral from 2 to 5, and that will equal f of 5 minus f of 2. Now, this is a calculator active question. We can tell that by looking at the answers that we have. Also, it's question number 77. It's later in the exam where we get to use technology. So we're going to evaluate this integral on the left using technology. So I thought we would use the TI-84 to do that. And on the 84, there's some really nice features to enter integrals. If you press the alpha button, all the buttons at the top give you lots of nice choices, lots of different things we can choose from. For us, we are going to choose the function integral. And I know, hey, this looks just like I would. I've got a lower limit and a right-hand limit. The format of it looks really nice. So I'm going to enter the integral from 2 to 5 of the function square root of 1 plus 2x raised to the third power. And then we need to take it with respect to what variable? With respect to the variable x. We press enter, and the calculator returns an answer. Pretty nice. This is one of the calculator ideas that the calculus writers expect students to be able to do. So I'll go ahead and import that answer directly into our equation that we have here. And if I go ahead and solve for f of 5, this is what we come up with. We always want to remember we want to go to 3 decimal point accuracy. And since it's multiple choice, it's able to match up pretty well. The answer is choice A, 29.005. Tom, anything to add on that? That's one of the calculator skills, right? Being able to evaluate an integral that's definite.
Yes, and I just point out that on your second line there, a student might be tempted to try to anti-differentiate by hand, that left-hand side, but that's going to be a really tough one to get. This is one where really the fundamental theorem of calculus is the way to go, and then the calculator is a great aid in calculating that definite integral.
Right. So I'll always remind your students, if you're on the calculator part of the exam, please use your calculators. Show the integrals you're evaluating, but please use those calculators. Another question is from 2008. This is a piecewise function. F is shown above in the figure, and we are told that we have function g of x equals the integral from -2 to x of f of t dt. Which of the following values is greatest? So our function g is accumulating from -2 to some variable x. This is a really great way to view accumulation in terms of the technology. Let's look at the TI-Nspire first, and then we'll take a look at the TI-84 as well. On the Nspire, what I have here is, not that one. I've got the piecewise function here. And what's nice is I'm starting at -2, and I'm accumulating to this point x. And then down below, it's actually telling me what that is. So as I drag point x across, we can see the accumulation happening, and noticing that we're getting a larger and larger value down here. And in fact, if I were to start at -2 and accumulate backwards, well, again, it emphasizes the point that we'd be getting negative values this way. But we were asked to find the largest value that we could get. At what value of x does this occur at? So as we're dragging across to the right, x is getting larger and larger. In the top left corner, I kind of put in what the value of x was. And we notice that once we get past x value of 1, our we've got a biggest value here of 4, but as I go past that, it starts to decrease because we're accumulating negative amounts here. So we were asked to find when the largest amount is, which would be at the value when x is equal to 1. Now on the TI-84, it also looks really good. And what I like on this one is actually being able to view the accumulation as it happens. Students so many times just don't have these visual pictures in their head. And if they could have this in their mind's eye, I'm actually accumulating as I'm going. You know, thinking about those very, very thin rectangles that we talk about for numeric integration, it really gives them a good picture in their head. Now the 84 looks really great as well on that. On the 84, what we have to do is enter the function, and I went ahead and entered it in. Using the 84 for piecewise is not that bad. What you do is you type in the first piece, and then you multiply it by what its domain would be. Our first piece was this was its domain, and you keep adding each piece as you go. I've got our graph displayed here. Now to evaluate the integral here, I'm going to evaluate from -2 to -1, just so you can see that. We're going to go second, calculate, and then choose integral. And it prompts me what is the lower limit. Oh, the lower limit is -2. And I just want to explore to -1. And what's nice on this is that it actually shows it accumulating. It doesn't just automatically appear as shaded. We'll see it slowly accumulating as we go. And again, that visual is really powerful, students, to see. And so with this question, students could go back through and keep trying different values until they see what gives us the largest answer, which we would decide would be G of 1 would be the greatest value of that. Tom, anything to add on this one at all, or?
No, I think you know, one thing I point out, I think this is probably from the non-calculator part of the exam.
Yes.
But what you've illustrated, Patrick, is you know how you can use the technology to fuel a discussion in class about various aspects of these functions.
Right, and so then maybe a really good link then be how would we find this out? And it'd be using our geometric formulas, right? Our trapezoids and rectangles. Very good. Okay, so let's take a look at the next question I'll talk about. It's from the free response. It seems every year on the exam, it seems that there's some type of in and out rate question. We're told that the rate at which rainwater flows into a drain pipe is modeled by the function R, where R of t is defined as such. And t is measured in hours from 0 to 8. So this is really a nice thing to know. That's our domain from 0 to 8 inclusively. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by D of t. So D for drain, R for rainwater coming in. And that is modeled by D of t equal to this. Now, the one thing that students tend to miss on these questions, and they need to read, right here, there's an initial value portion that's hidden in the topic. It says there are 30 cubic feet of water in the pipe at time equals 0. Some students will be working through all of these questions, and they'll miss that. So they want to be careful when they're reading it. They want to underline this and circle it so they see it later in the question. They will definitely need it. So we're going to look at part A. Question says, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval from 0 to 8? Well, R of t is the water flowing into the pipe. So we're going to evaluate the integral R of t from 0 to 8. So I'm going to go ahead and do that on the TI-84. So the first, oh, by the way, whenever you do your integrals on the graphing screen like this, this is drawn on. So what you have to do is, first off, quit out of that window. And then what you have to do is go second, draw, and choose the very first choice here, clear draw. And what that'll do is it'll clear up that shading. That shading will disappear. And if we notice down in our windows here, it definitely has disappeared. Okay, so let's go ahead and evaluate that integral, that R of t, from 0 to 8. Now, one thing that I've done, and it's a helpful technique. I picked this up from Dixie Ross. It was type the functions into the y equals screen. Y2 for me is going to be the rainwater flowing in, and Y3 is going to be the rainwater flowing out. Now, I need to make a note here. When you're writing things on the AP exam, do not use Y2 and Y3. Use what the AP writers have done. They have said we're using R of T and D of T. But this helps us avoid parenthesis errors later on, and it saves a lot of time from having to constantly retype this in over and over and over. So Y2 is my rainwater going in. So I'm going to go ahead and go to my home screen here and press Alpha, Window, and I'm going to choose Integral again. And our limits are from 0 to 8. And the nice thing is, since our rainwater flowing in on our calculator, we defined it as Y2, I'm going to go ahead and press Alpha, Trace, and choose Y number 2, which is number 2 here. And DX. So this is really clean and really nice. It helps the students type things in much faster, much more efficiently, and perhaps they'll make less errors. We press Enter, and we're able to come up with what the answer is. Now on the Nspire, it's done in much the same way. Oops, sorry about that. On the Nspire, what we would do is I've gone ahead and entered in my rate flowing in is F1 of X. And so on a calculator screen, there's two ways to get this. One way is to press the template button. Another way is to press Shift+. It's a quick way to get it as well. I'm going to go ahead and type in 0. The tab button is nice because it moves you from space to space. And our rate in, the water flowing in on my Nspire question here was an F1 of X. So if I press variable, I can find F1 pretty quickly, or I could just type in the letter F and the number 1. Now I need to say of X, so I need to put an X there, and then DX, and that will go ahead and result in the same answer. Now you might say there's not enough decimals showing here. On the Nspire and on the 84, if you press the up arrow, you can recall what you've previously typed in. But on the Nspire, to see the remaining digits here, press Enter, and we'll see all the digits that the Nspire calculated it to, which is pretty nice. Again, the answer would be to 3 decimal points. We'll take a look at the part B of this, and this says that the amount of water in the pipe, is it increasing or decreasing when time equals 3? Give a reason for your answer. Many students, okay, increasing, decreasing, I better take the derivative. They need to be careful with this question because this is a rate already. We're told the rate at which rainwater flows into a drain pipe. So this is already a rate flowing in, and this is the rate of water flowing out. So we just need to find out which one is larger when time is 3. The best way to do that is just to subtract those. Do R of 3 minus D of 3. We can do that pretty quickly on the 84. And on the 84 again, I've already typed in my rate going in and my rate going out. So I can refer to them as Y2 and Y3 on the TI-84. And that's exactly what I'm going to do. I'm going to go ahead and type in alpha, trace, and choose Y2. That is my rate going in. Now Y2 of 3, I want to know what's the value of that water flowing in when the time is 3. And I'm going to subtract alpha, trace, and choose Y3 of 3. Now on the exam again, do not write on the answer Y2 of 3 minus Y3 of 3. Instead, be sure to say R of 3 minus D of 3. I'm like, wow, that's negative. So that must mean that the water flowing out is larger than the water flowing in, the rate of water flowing in at that time. So since this value here is going to be negative, that must mean that R of 3 is, oh, hold on a second, Tom. I think I typed this in wrong. What did I do here? Yeah, okay, I've got these backwards, doggone it. Since this is a negative value, we would say that, and these should be backwards, D of 3 is greater than R of 3. So the amount of water in the pipe is decreasing. Please don't make that error on your exam when you do that. Since this answer was negative, D of 3 must be greater. My symbol's going the wrong way here. It's important to say at time equals 3 hours, because what this could occur, maybe at different times, different things are happening. Maybe at some point in time, R of 3 is greater than D of 3. So when time is 3 hours, it's not. Also, if we're provided units, we do want to use those. So don't say just at time t equals 3. Time equals 3 hours. Specificity, being very specific with our language is important on the exam. We're trying to communicate correctly. The last part I'm going to talk about here is at what time between 0 and 8 is the amount of water in the pipe at a minimum? Justify your answer. And a lot of times students see this question and they panic because we've been doing integrals here. And you just remind them, hey, in calculus, how do we find the minimum value of a function? And say, well, minimum values occur at critical numbers. Oh, what are critical numbers? Critical numbers are when the derivative of a function is 0 or undefined. So we need to come up with a function that we need to find a minimum of, which is the amount of water in the pipe. And this is where this piece comes in handy. We need to make sure the students remember this. So please, when you're teaching your students and instructing them with these questions, when they see an initial value in this fairly large paragraph, underline, circle it, identify it somehow, because they will miss it. It looks like words to them, not like the functions that we have up here. So we need to come up with something describing the amount of water in the pipe. Well, the amount of water in the pipe is going to be the initial value plus an integral from 0 to some unknown t value of the rate of water going in, subtracting the rate of water going out. So to figure out this, that's our function we want to know. We want to find the minimum value of it. So as the students remembered, oh, we need to find critical numbers. So let's take the derivative of this. Well, the derivative of 30 would be 0, and the derivative of this integral, that's applying our fundamental theorem of calculus. AP loves to have lots of ideas into one question. The derivative is going to wind up being R of t minus D of t. Now, this would never be undefined in our interval, so we're going to find out when does this equal 0. And this is another thing that the AP writers expect students to be able to do on their calculator. This is a calculator question. If you think about it, when would R of t equal D of t? That's a lot of work. So we're going to use technology to come up with that. And I'm going to use that on the Nspire first. And on the Nspire, what I've done is I've gone ahead and graphed both functions. And I need to find out where they intersect, because that's when they would equal 0, right? When they both add up to, when one minus the other equals 0. So on the Nspire, we will press Menu and choose Analyze Graph and choose Intersection. And it prompts us for a lower bound. And so I'm going to click somewhere to the left of the intersection point and then slowly drag through the intersection point. Now, once it passes the point, it tells us, hey, there's the intersection right here. And remember, we would like to have at least, we want as much accuracy as possible. Final answers, we need 3 decimal points, but earlier on, we need to be more accurate than 3. So the way to see more of these values is to hover on top and then press the plus button. Every time you press plus, another decimal point shows. If you press minus, we lose decimal values. So we could see that, hey, this is our intersection point. Now, to do the same thing on the Nspire, on the TI-84, I've, again, already have my 2 equations typed in. So I'm going to go ahead and make them active by making sure that equal sign is selected for both of them. And I need to manipulate the window a little bit because our window setting, the time was between 0 and 8. So I'm going to choose 0, and then I'm going to choose 8 for the maximum value. And one of the great features on the Inspire and on the 84 is once we type in the domain, which is 0, 8, the calculator can automatically figure out these range values, which is really nice. And to do that, we just press Zoom, and we are going to choose Zoom Fit. And here's our two functions being graphed out. There's the rate of water going in, and here's the rate of the water going out. And notice it took our domain, so our smallest value to the largest value, and found the appropriate Y values within that domain to make the window look good. Kind of nice. To find the intersection point on this, again, it's something that we need to have students be able to do on the calculus exam. They'll choose second, trace, and they will choose intersection. And what I tell my students is if there's only two equations on here that have been graphed, it's fairly quick. Move your cursor to the intersection point and then just press enter 3 times. And we see it's working, and there's our value, right? There's our X value that we needed to get. So we've got two critical values. And what we would do then is we would think about this, say, okay, minimum values could occur when there's a critical number, but also this is a closed interval from 0 to 8. The minimum value could happen at 0 or it could happen at 8. So we need to use a table. This feels a lot like extreme value theorem, which it is. I've put my critical number in there also when t is 0 and when t is 8. We need to compute the amount of water in the pipe. Now, when time is 0, well, that'd be the integral from 0 to 0, which is 0 plus 30. So this answer here would be 30, but we need to figure out what these other two values are. And to do that, we're going to go ahead and go back to the calculator, and I'm going to do this one on the Inspire to evaluate. Well, we've already shown how to do it on both. On the Inspire, these windows talk to this page here. And what I want to do is I want to go ahead and choose integral, but first 30 plus the integral, so shift plus is a really quick way to get it, from 0 to, I'm going to choose the first one, which was 3.271658. Oops. So when I'm an old school typer, I can't look at the screen and type at the same time. So sometimes I make errors like that in class. Kids think it's pretty funny. So 3.27165.58. And again, we're going to be finding out the, when you put in the in minus the out, and the in on the Inspire was F1 of X. Again, I could just type in the letters F1 of X minus, or I could have just pressed a variable to find it as well. Either way is okay. Minus F2 of X dx. Now, one nice thing is since this calculator has decimals up here in the numerator, we're going to get back a decimal answer. So this is our answer. And again, our final answer, we only need 3 decimal points. I do need to change this integral to go from 0 to 8. So one nice feature on both calculators is that we can press the up arrow and change them to be whatever values we would like. So I'm going to go ahead and press the up arrow, press enter, and then change that upper limit to be just an 8. Whoops. To make sure I'm going to get a decimal answer, I will press Control Enter to come up with that. And it turns out that we actually find a pretty large value. The question was asking for what is the minimum value of this function. And so the absolute minimum value would have been when t was at 3.27, because that's the value that gave us 27.9646. Dick, do you have anything to add to this question? There's a lot of stuff in this question, and I guess we could go on for quite some time, but there's some things that we need to make sure that the listeners are kind of cued into.
No, I think you covered pretty well, Patrick.
Okay. Okay, so one last thing I want to do here before turning over to Dick is to take a look at slope fields on the TI-84. And the TI-84, there's lots of programs that are out there that you can use to get slope fields. You can look on the Activity Exchange, you can search anywhere you like. I was searching along and found a program called Slope Field 3. Pretty brilliant programs that are out there. And what we do is we run the program, and it gives you a nice little menu to choose from. And it does have Euler's method. Lots of these programs have all kinds of things in there. We're going to go ahead and draw the slope field, and we can enter in any type of slope. Oops. Can't really draw it until we type in the slope field, I would think. Oh, okay. Pretty nice. It's drawing our nice line segments very quickly to evaluate. Not sure what slope field I've entered in here, but we'll let it run its course. I do like how the 84 graphs things a little bit slower so that students can kind of see what's happening right away instead of everything just popping right out at them.
A lot of these refer to Y1 for the thing they're taking the slope field of, so that might be where you'll find.
Right. Oh, here we go, 3. Let me go ahead and choose that. Yeah, I guess it was trying to use my piecewise function, like you said, Dick, Y1. All right, let's make something interesting. Let's type in X minus Y. So alpha Y. And so hopefully this will kick us out slopes of 0 when X and Y are the same value, right? So I'll choose enter. And now we're back to our menu here. So I'll choose 1 to draw the slope field. But again, like Dick was saying earlier, without technology, this would be a tough thing to visualize. I always kind of think of it being like a wind map showing which way the wind is blowing. I don't want to take up too much time on this, but we could also, on the window settings, if I had changed the window settings to be something a little bit nicer, we could have seen from negative to positive as well. Okay, well, Dick, I'm going to turn it over to you.
Okay.
And, okay, I think you have, you have it now.
To me. Okay.
There you go.
All right. Okay. Thanks, Patrick. So I'm going to talk some more about slope fields, and I thought what I might do is just take a little bit of time to explain the idea behind the slope field. It used to be that slope fields were a topic that if they were covered at all, it was in a like sophomore or junior level, college level differential equations course. I think with the advent of technology, it's really made the topic very accessible. And to me, I'm using slope fields. I don't wait for differential equations to do them. I actually do them as soon as we're starting to talk about antiderivatives. So the idea behind a slope field, let me go ahead and maybe illustrate here with I'll insert a graph page. And I'm just going to put in a regular function here into F1. The function I'm going to put in is x squared minus x. Okay, so let's graph that. Okay, just a regular little parabola here. And what I want to do is just focus our attention on a small piece of the graph right at where x is equal to 2. So let's see, when x equals 2, f of 1 of 2 is 2. So I'm looking at the part of the graph right around the point 2, 2. And in fact, I'm going to take a close-up view of that by going ahead and zooming in, and I'm going to use the zoom box. And so with zoom box, I'm going to make a very little graphing window kind of around that 0.22. So you can see I've made just a little box there, and what that's done is zoomed in on the graph, and what we have now is this zoomed in version of the graph, and we see something that looks like a straight line. And that local linearity of a differentiable function, if I was to actually try to find the slope of this line, I'd find it would be very close to 3. Okay, I'm thinking that I know the derivative of x squared minus x is 2x minus 1. Evaluated 2 would be 3. And so up close, that graph looks like a little line segment of slope 3. Okay. I'm going to show you a little clip actually from a document. This is one of the Explorer books around the TI-84 on slope fields. And it's taking that idea, okay, I'm hoping you're able to see this. What we've got is a picture of that graph on the 84 of x squared minus x in this zoomed in version. And down here is a picture of just one little snapshot of the function localized at 2, 2. The idea of a slope field is to take this idea and do it over and over again. Suppose you knew what the derivative was at each point. You could graph a little line segment at each point reflecting the information that the derivative tells you, which is the slope. So you get a bunch, basically a lattice of these little slope segments. And from those, you can then try to visualize what the graph looks like. Okay, so let me return back to Nspire and see how we might do this with a slope field. Now the 84, you are going to need a slope field program, and Patrick illustrated one. There are a lot of different versions out there. That Explorer, that guidebook that I described, has a TI-84 slope field program in it too. I'm going to go ahead and get a new page here and insert a new graphs page. But now I'm going to pick by graph entry edit here. I've got all my different graphing types, function, relations, parametric, etc. Way down at the bottom is differential equation. Differential equation is where you would find your slope field plotter. And so now what I get something different than the f1 of x there. Now I have y1, and if you look closely, you see that little prime. It's actually, this is the derivative of y1. And I'm going to put in an expression for what the derivative is, okay? So for example, suppose I put in 1 divided by x. It's kind of a classic. So I want the derivative of my function to be equal to 1 over x, and I want to try to visualize what that original function would look like. So when I hit enter, what it's done is use that information. Let's see if this makes sense. So near x equal 1, let's see, 1 over x would be 1 over 1 would be 1. I should be seeing line segments that have a slope of about 1. If x is negative 1, I should be seeing line segments that have slope of negative 1. When x is larger, say around, let's say, x equal 3, the slope should be gentle, 1/3. And you can see the further out you go in the x direction, positive, the less steep these segments become. On the flip side, if x's are negative, again, they're not very steep. The further away from 0 you get, the less steep they are, but now they have negative slopes, okay? Now this is one that I know our audience probably knows the punchline to. This is the differential equation that gives rise to the natural logarithm function. And when you have a slope field, if you have a candidate in mind of something you think might be an antiderivative that fits the slope field, you can actually plot it on top of the slope field, which is really instructive. So what I'm going to do here is go back to my menu, go back to the graph, and this time I'm going to plot a function on top of the slope field. So I was thinking natural logarithm of x, Oops, pardon my typing here. There we go. I think I finally got it right. And there's a graph of the natural log of x, and you can see, okay, it doesn't go through all the slope segments. This is just a lattice of sample segments. But in any column here of segments, you'll notice the graph in that column looks parallel to those segments. So this is a graph that fits that slope field very well, okay? Let's see, that's not, I wonder what we would need to fit the slope field over here. Notice this is only fitting for positive x's. Let me see if I could graph another function. Okay, actually let me just do it. Let me just bring up the graph editor. And I'm going to put in a second function now. This one will be the natural log of the opposite of x. And I'm also going to add on 2 to it. And with the slope field, you can kind of help get across the idea that there is that arbitrary constant involved because these vertical translates are going to fit that slope field just as well for a derivative that's in terms of x alone. So if my derivative it only involves x, then for each value of x, all the slope segments for that value of x should be parallel. They should all have the same slope because it only depends on the value of x. All right? Now I'm going to jazz things up a little bit here. I'm going to insert another graph page. And this time, let's again bring up our differential equation plotter. And in this time, I'm going to put in a differential equation that is in terms of y. Now, my y here is labeled y2 prime. So if I'm going to refer to y, I need to use that same labeling scheme. So I'm going to use a very simple differential equation. This is y2 prime is equal to y2. The idea being I'm looking for a function whose derivative is itself. But what would the slope field for that look like? Now we get a very different slope field, and now our, let's see, what did I do here? I think I've got, that's the same one we had before. So let me try to recover here. I think what I need to do maybe is check it. And okay. And let's see. Well, you know what? I'm going to start off fresh. How about that? Let's just get a fresh problem. Add graphs. Thanks, everybody, for your patience. Okay. All right, so let's put in y1. So y1 prime equals y1, and that's what I was looking for. So again, thanks for your patience there. So now notice that the rows of line segments here have the same slope because each value of y is determining the slope. So when y is a small positive number, we're getting a small positive slope. As y gets larger, we see steeper positive slopes. When y is negative, we get slopes that are steeper and negative, okay? Let's see, I think a punchline here is the exponential function is a function we could plot over that. Let's try that. And put in e to the x, okay? And what's interesting here is one can explore and find that the arbitrary constant that's involved here is not an add-on, but actually a multiple. So multiples of e to the x, constant multiples of e to the x will also satisfy this differential equation. All right, so if I graphed yet another one, for example, how about 2e to the x. There we go. And so we can see both of those are fitting the slope field. Our labels are getting a little bit on top of each other. Okay, so I found that slope fields really are powerful for talking about and visualizing solutions to differential equations. The idea behind, well, first of all, let me just take a little bit. I'm going to go back to a document that I've got in Acrobat Pro. A really good assessment activity around slope fields would be you could use either TI-Nspire to generate a slope field, and then here I've got a collection of slope fields, and then give the differential equation that those slope fields come up from, and then ask students to match those up. And just want to talk about some of the skills that come into play here. For example, here on number 3, this slope field, whatever that is, notice that the rows appear to be parallel segments. And that's suggesting that this differential equation is something of the form dy dx is something in terms of y, because it looks like it only involves y. Over here on number 4, the columns of line segments appear to be parallel. So that suggests that that differential equation is in terms of x alone. Dy dx is a function of x. Number 1 and number 2 up here, these are probably involving both x and y, all right? And let me just go back to the Nspire, and we'll do one last slope field here. And so we'll add, this will be a differential equation in terms of both x and y. And it might seem a bit exotic at first, but it turns out this is one that students will have encountered in a sense when they've done implicit differentiation. So what I'm putting in is y1 prime is negative x over y1. And now I'm getting a slope field, and it looks like the curves that would fit this slope field would be circles, concentric circles about the origin. Well, if you think about it, if you take a circle centered at the origin, x squared plus y squared equals 9, for example, if you use implicit differentiation, you get dy dx equals negative x over y. So they have encountered those, okay? The last thing I'd like to illustrate to you is when you have a slope field on the differential equation plotter, you also have an option of putting in an initial condition. And so that would be one point that lies on the curve. And then what the differential equations plotter will do is it'll actually use a numerical method to kind of bootstrap a solution by basically plugging in the initial condition point, finding the slope, then taking a small step in the x direction, and using the slope to figure out a new y value, and then repeating the process. This is essentially Euler's method. Okay, now the one we have here will do some funny things if I enter in an initial condition. I'll go ahead and put in an initial condition down here. I'll put in 3, 4. And what it's done is, I don't know if you can see this fat brown point here. That was my initial condition point. What it's done is it's tried to follow the slope field by taking tiny values of delta x, and it finds, using the slope, it finds out what the predicted y value would be. What's going to happen, though, is when it hits where y equals 0, negative x over y, that's going to be an undefined slope. The delta x is going to get it tripped over to another solution curve. So you see this one semicircle that looks pretty nice, but then once it's stepped off that circle, it starts landing on other circles. Okay, so that's something where Euler's method is coming into play. All right, so let me maybe show one other slope field here. Let's see, let's go back to this one and actually go back to a 1 over x version. Okay, and here we go. Again, it was taking that same initial condition and using the differential equation dy dx equals 1 over x and plotting an approximate solution curve using Euler's method. What's really cool here is I can actually change the initial condition point by actually grabbing it and dragging it. And so I can see different solution curves. Now, do you see that wild stuff happening over to the left of x equals 0? Again, we've got a vertical asymptote here. And so when the increment is gotten over here into the negative x's, and when I say increment, the delta x is actually extended in both directions. When it steps over that asymptote, it ends up on a different solution curve. So if you have discontinuities in the expression for the derivative, that's going to be something that Euler's method will be sensitive to. Is it's when they hit those asymptotes and steps over them, you'll end up on different solution curves. Okay. Well, I think I've probably just about exhausted our time. I do need to turn it back over to Michael so he can do some housekeeping here at the end here. So I'm going to stop sharing and turn this back over to Michael.
Thanks so much, Tom. As we begin wrapping things up tonight, if you have any last-minute questions for Pat or Tom, please try to get those asked. I know they'll do their best to get those questions answered. We have some resources available on our website, education.ti.com, that I'd like to share with you. If you move under the Professional Development tab and slide down to Webinars and Tutorials, there's some really great stuff here. So on the left-hand side is the live webinars, and if you click on that, you'll learn about all the future webinars that we have coming up this spring. I know we have 2 more calculus-specific webinars scheduled, I believe 1 in March and 1 in April. So you can register for those, and if you can't make it, because you register, you'll automatically receive a link once the recording is available with a link to the recording, the documents, and also the certificate as well. And then you can check our on-demand webinars, where all of our webinars that we've had so far are archived, and you can filter those. So if you're looking for something that we've done, say in the past, specific to calculus, that's really easy to do. And then on the right are the technology tutorials. And I really like that Pat and Tom showed our 2 different platforms tonight, the TI-84 platform as well as the TI-Nspire platform. And so I thought I might give a shout out to our friends over at Atomic Learning. They put together some really great videos for both the TI-Nspire as well as the TI-84 technology as well. So you can say, click on the graphing, and under the TI-83 plus TI-84 plus graphing calculator family, there's links where you can get additional resources and tutorials for these really short videos that they put together to remind you of maybe how to do something that you haven't seen for a while, or maybe to learn some new technology skills. Again, that's both for the TI-83, 84 plus, as well as the TI-Nspire. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, and we really listen to your thoughts. So we hope you share those thoughts in the post-webinar survey. I know I'm excited about the T-Cube International Conference this year. If I had to guess, I bet both Pat and Tom are just as excited as I am. I know they'll both be there. In fact, whenever we were in our practice session tonight, they were talking about the calculus sessions that's being offered. Tom, would you mind just talking for a few seconds about, I think it's a power session that's being offered at the International Conference this year. Can you speak to that at all? And Tom, just so you know, you're still muted.
Thanks, Michael. Yes, happy to put in a plug for some activities at T-Cubed International Conference that are going to be particularly of interest to AP Calculus teachers. There's all day on Saturday of the conference, that's March 11th, we'll actually have basically a calculus conference within the conference. So we've got a slate of speakers, including David Bursood, who used to be the chair of the AP Test Development Committee, as well as he's a former president of the Math Association of America. Deb Hughes-Hallett, who's one of the authors of one of the most influential calculus textbooks out there, and some other great speakers that will take up the entire day on Saturday. And then on Sunday morning, there's a special panel that includes Stephen Davis, who's the chief reader for AP Calculus, Vicki Carter, who's one of the chairs of the current AP Test Development Committee, as well as a T-Cubed instructor, Craig Wright from Educational Testing Service, and others will be on that panel, and they'll be sharing some insights into the AP exam and its grading, and some things coming up that are new in the AP program. So it's a fantastic opportunity for AP Calculus teachers. The Calculus conference, within a conference, it's okay to kind of bop in and out of that. You can come in, attend a session, but if there's other sessions on the TQ program that you're also wanting to go to, it's fine to go in and out of that special Calculus conference session. So hoping to see some of you there. Back to you, Michael.
Thanks so much, Tom. Thank you. As we mentioned earlier, tonight we're giving away to one lucky winner a T-Cubed International Conference registration. And tonight's lucky winner is Cheryl McLaughlin. So Cheryl, congratulations. We'll be in touch over email within the next couple of days to give you a little more information. But we really hope to see you as well as everyone else at the T-Cubed International Conference this year in Chicago. Please feel free to continue any conversation that you may have already had tonight or that you want to start on any of the major social media outlets. To receive a certificate of attendance, go ahead and click that link in the chat window. Also listed is a link for the documents that were used tonight. In case you missed them, feel free to just check your email in a couple of days. You'll automatically get a follow-up email again with a link to the recording, a link to the certificate, as well as a link to the documents. If you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. If you're in need of any post-webinar follow-up, please feel free to give us a call at 1-800-TI-CARES or send us an email at ti-cares@ti.com. We'd love to hear from you. Thanks so much, Pat and Tom, for everything you shared tonight. I was just reading some of the comments in the chat window, and it looks like I'm not the only one that was excited about some of the information that you guys shared. So, again, thanks so much for everything. We really appreciate it.
You're very welcome. It was a lot of fun.
Again, thanks so much, everyone. We hope to see you back online real soon. Have a great night.